When two massive objects collide, physical reality is complex. A head-on impact between a truck and a motorcycle creates a web of mathematically coupled forces. We cannot analyze these dynamic systems in their raw, natural state. The volume of overlapping data makes direct calculation impossible. To manage this complexity, we must isolate individual objects and strip away the physical environment. This abstraction is the free body diagram. It is a protocol that converts real-world physical interactions into discrete geometric representations. The mathematical engine for this translation is Newton's second law. The net force acting on an object equals its mass multiplied by its acceleration. This equation maps physical geometry onto linear algebra, translating spatial vectors into a coordinate system. Without this orthogonal translation protocol, solving complex mechanical systems is impossible. With it, physical interactions can be resolved into a series of equations. The starting point for this translation is an inertial baseline. Newton's first law establishes that if the net force on an object is zero, its acceleration is also exactly zero. Zero acceleration does not always mean the object is stationary. It indicates a constant velocity, whether that is 60 miles an hour or zero. A resting object on a flat surface provides the most common baseline for analyzing balanced forces. This diagram shows the forces acting on a block at rest. The block's weight pulls downward, opposed by the upward normal force from the table. Because these forces are equal and opposite, they are often misidentified as a third-law action-reaction pair. They are not. The normal force and the object's weight are both acting on the same block. This creates equilibrium, but it does not satisfy the requirements of the third law. A third-law pair requires two interacting masses. Object A applies force to object B, and B applies an equal force to A. Here, the block pulls upward on the Earth, while pushing downward on the table. The primary utility of the free body diagram is that it forces the isolation of a single object, filtering out external reactive forces that would otherwise compromise the calculation. Newton's second law is applied by decomposing the net force vector into independent scalar components for the x and y axes. This schematic illustrates an external 20 Newton force applied at a 30-degree angle, disrupting the simple parallel alignment of our baseline. Using trigonometry, we resolve this angled pull into a horizontal cosine component and a vertical sine component. Analyzing the y-axis reveals that the angled pull is lifting the block slightly. Consequently, the upward normal force from the table is no longer a static match to the weight. The normal force is now a dynamic value. To maintain vertical equilibrium, it adjusts to equal the total weight minus the upward component of the pull. On the x-axis, the horizontal pull is opposed by a vector pointing backward, kinetic friction, which resists the sliding motion. The value of kinetic friction is determined by multiplying the coefficient of kinetic friction by the normal force. Because friction depends on the normal force, the horizontal x-axis calculation is mathematically coupled to the vertical y-axis equilibrium. This orthogonal translation demonstrates that the horizontal motion of an object is always mathematically linked to the vertical forces acting upon the system. The tools of the free body diagram scale to model dynamic environments where forces are not constant. Applying the protocol to a skydiver in freefall, we first establish the constant downward vector of weight, which is mass times gravity. Opposing this descent is an upward vector representing aerodynamic drag. The drag equation contains several variables, but its defining feature is that the force increases with the square of the velocity. On the vertical axis, the net force is the downward weight minus the upward drag. This difference dictates the mass times the acceleration. As the skydiver falls, their velocity increases, causing the upward drag force to increase exponentially. As the upward drag vector grows, it offsets a larger portion of the downward weight. The net vertical force is shrinking. Because the net force is shrinking, the acceleration must decrease, even as the object's speed continues to rise. Terminal velocity occurs at the exact moment the increasing drag force matches the weight of the skydiver. At this point, the net vertical force is zero, and acceleration drops to zero as a result. Even in a highly complex, nonlinear system, the object has successfully returned to the foundational baseline defined by Newton's first law. The skydiver now moves at a constant velocity, illustrating the profound consistency between the fundamental laws of motion.